Hey, students, just got a question from a tough one. It's chapter 5, and it's from the Advanced University Physics book, so that's chapter 6 in that book. And it's 103, so it probably involves here some calculus, and sure enough, I can see time variations and position and velocity. So I'll put on my calculus hat here and start giving that some thought here. But let's read the problem. It says here, located at the origin, an electric car of mass m is at rest, okay, and in equilibrium. Now, then it says a time-dependent force is applied at time equals to 0. And its components are given by this. And so this is the force, and this is the force in the x direction, and this is the force in the y direction. And then there's p and q and n, and they're constant. So they don't really tell us what they are. This could be like, 7 plus 3t. And then this could be like 4t. But we don't really know what those are. And so we're just going to treat them like constants. And so this would be more of an abstract answer than a numerical answer. But it says find the position and the velocities. And so the first thing I guess I'm going to do, the part that has to do with the chapter really here, is Newton's second law, which says you need to take the force and divide it by mass. But let me also put little x here components here, because as you heard me say many times, the best way to handle these is to do one-dimensional twice, okay? So this would kind of be my first step to say, okay, what is the acceleration in the x direction? And so you would take the force and divide it by m. And so in the x direction, here's the force. So if I divide that by m, I get p plus nt divided by m. And I don't know if it's necessary quite yet. But I will. I'll break it down into its two pieces because, m is also another just constant. So this would be just a constant plus some constant multiplied by time would be the acceleration in the y direction. The x direction. And in the y direction, I can do the same thing. So this is a q over t and then divide by m. And so I'll just write it as q over m times t. Okay, maybe I'll just put a kind of little circle around that. So this is the acceleration in the x direction, and this is the acceleration in the y direction. Okay, now I can get to right here where it says find the velocity vector. So that means what I need to find is the velocity in the x direction and also the velocity in the y direction. And this is where our calculus comes into play. Maybe I'll come up here and do our definition, but acceleration is how the velocity changes with time. And so if I take the time and move it to the other side, I get acceleration dt is equal to the derivative of velocity. And then we do this integral or antiderivative. And this is the key thing here. You take the antiderivative of this, you just get velocity. And so this is really saying the way you get velocity is you integrate acceleration. This should look a little bit like the chart I said, which if you have position, you can get to velocity by taking the derivative, which means in reverse, you can get to position by integrating velocity. And likewise, to get from velocity to acceleration, you can take its derivative, which of course means the inverse operation is to integrate or antiderivative of it. So I'm doing, I guess, this part of my little chart where I'm saying I know an equation here for the acceleration. How do I get velocity? And so I integrate. So let me integrate this thing, which is p m plus n over mt dt. And fortunately, this is kind of that calculus review where I said, okay, how do you treat constants and how do you treat additional terms? This is what we mean by a linear operation. So this first one, we could pull the constant out in front, Pm, and just have an integral of dt. And the second one, we can pull out the constant n over m and have an integral of t dt. Okay, and so that's what I meant in the calculus review by a linear operator. You can pull constants in front of the operator, so this integral, and then you can also break it into two separate pieces. So I'm going to then do the easiest of integral, an integral of dt, and if you remember, you can think of this as t to a 0 power, so you add 1 and divide by the new exponent. And then this one here, which is t to the 1, you now add 1 to the exponent and divide by the new exponent. Now technically, let's not forget this, that there would have to be a constant. And I guess technically even a constant for each integration. However, if there's some constants and another constant, why don't we just add them together and call it some other constant? And so this would be the equation for the velocity in the x direction. Now, we can also use something very important here. It says it's located at the origin and is at rest. So in other words, when we put in time equals to 0, so if I say what is the velocity when time equals to 0 in this equation, this first term is 0, the second one is 0, and you just end up with a constant. But remember, the problem says this is supposed to equal 0. So this would tell me my constant is 0. Yay! And so I guess I'm kind of out of room on that page. Let me switch over to my yellow pad here. Okay. So here's my x, here's my y. And so if I take what I've learned so far, I have an equation for velocity in the x direction as p over mt plus n over m, and I'll just put it back together and put that in the numerator, t squared. I guess I can do that one too. And then I don't need to worry about the constants. The constant came out to be 0. So probably makes it a little easier that the constant came out to be 0, but sadly it also means that if you were careless with your math and forgot about the constant, you would actually get the right answer. And that doesn't make a good problem for a teacher in order to grade the students to see if they're doing it right, because they get the right answer but are kind of missing something. And yeah, that's not a good strategy for a problem. But anyways, it's the way this one works out. Now, let me do the same logic over here for the y direction. Again, this would be the integral of the acceleration, which we said was q over mt dt. In fact, I'll pause. Notice that I'm doing what I said. Just do our one-dimensional motion twice. So I did it once in the x direction, and I'm going to do it again in the y direction. So this would be a q over m, and then the integral of t dt, and then this is a q over m, and then if we add 1, it's t squared over 2. In fact, this looks kind of a lot like this second term there on the x one. And then let's not forget that there is a constant. But that same logic, if this is the velocity in the y direction, at time 0, we're supposed to get a velocity of 0. And so this first term is 0 and then plus the constant. So that would tell us that the constant for this y integration is also 0. And again, for the same reason, that's probably not a good way for a teacher to set up a problem, because again, if somebody forgets the constant, they actually get it right. But that means that I can put over here that the velocity in the y direction is q over mt squared. And so I guess I've done half the problem where I have gotten the velocity as a function of time. And they put a little arrow, and that means there's an x component and a y component. Now, let me just turn the page for a moment. There is an advanced way to write this. Actually, let me tear this off. And you don't need to do this. But the advanced way is to say, write the x component with this symbol I hat, and then say also at the same time the velocity in the y direction with this symbol, which we call j hat. And you don't need to do that. For this problem, you can write this. But I did look up, or I'm looking right now online, and it wouldn't surprise me. Let's see, where? Chapter 6. Oh, wow, this would be way down here. Page 103, or problem 103. Let me try to find it real quick so I don't waste your time. But it wouldn't surprise me if they wrote it like, yeah, they do, where they put the x component with a little I hat and plus a y component with a little j hat. And this is how they write it. So you don't need to write it with this fancy mathematics of I hats and j hats. That's you might be familiar with it. It's not all that critical for us. Let's just do this, and we'll have a one column, which is our I hat, and our other, which is our j hat. Okay. All right. Well, let me keep going, because as the problem says, not only do we want to find the velocity of the function of time, so both the x and y component, but we also want to find the position, and get an arrowhead, so it has both the x and y components. So let me just point out then that x would be the integration of the velocity in the x direction dt. So doing this integral, I've got a p over an m and a t plus an n over an mt squared dt. And if I actually do this integral, same logic, I'll break it into two pieces with a plus sign in between them, okay? And then the constants I'll pull out, so there's p over m. And so I'm doing an integration of a power function. This would be t to the 1 power. So I add 1 to the exponent and divide by that new exponent. And then likewise here, I'll pull out the constants. And then I have the integration of t squared, so that becomes t cubed over 3, and then, of course, plus a constant. But again, if you look at this, when time is equal to 0, they say the position is 0. See, that's what it says right here. Located at the origin. So that means x and y are equals to 0. Okay? So if you put in time equals to 0, that first term is a 0, the second term is a 0, and then plus the constant. So again, maybe a little too simple, but they said that the constant in the x direction is equals to 0. So you can finish this calculation by saying the equation for the position is p times t squared over, and usually we write the number first, so I'll put 2m, and then over here will be a 3m on the bottom, and then an nt cubed, and I'll put a little circle around it, and so that should be the equation for the position in the x direction. And I think I copied it down wrong, and I apologize. Yeah, I was thinking there was a 2 here. So there should have been a 2 here, which makes a 2 here, which makes a 6 here. Actually, I got the, and let me look up at the answers. Did they get a p t squared over 2m? They did, and an n t, yeah, 6. Yeah, okay, good. And then, of course, they wrote it like an I hat and a j hat in the solution. All right, one last step here then. Let's do the velocity, I'm sorry, the position now, y, would be the integral of the velocity. Okay, and so the velocity, which is this one here, has a q over an mt squared dt. And so if I integrate that, again, constants can be pulled in front of the integral, linear operator. We now have a power, so we're going to add 1 to it and divide by the new one, and then we're going to throw in a constant. And then we're going to pause and say, well, okay, y is supposed to equal 0 when time is equals to 0. Again, because they say it is located at the origin. So it starts here at the origin. So if you put nt equal to 0, that first term is 0, and then you get a constant. So again, all 4 of these cases involving integrals, because we did 2 integrals to go from acceleration to position, and we did it for both x and y. So all 4 sets of integrals, we got a constant. All 4 of them came out to be 0. And like I said, probably not good that all 4 come out to be 0, because if a student got lazy and forgot about them, they would still get the right answer. All right, so then I can finish this by saying qt cubed over 3m. And oh, no, they got a 6. Oh, did I get lazy again and drop my 2? I think I did. Yeah, I'm so sorry. Back here, there was that 2m. Yeah, so I dropped it here accidentally and dropped it there. And I caught it here and put it back in, so glad I fixed that. And then let me just double check, 2m's, yeah, so that should be a 2m. That should have been a 2m. So then this should have been a 2m, and that makes ultimately 6m, and that matches the answer. So, sorry about the dropping those 2. It's got careless from one page to another. But here we go. There it is, and that should be the equation for position. All right. Good problem, tough problem, some fun calculus. All right, take care.